Let us now discuss about the Pareto optimality property in the quasi-linear domain. So as before, the notion of Pareto optimality hinges on the fact that every player should be weakly better off, and there must be at least one player who is strictly better off. And in this context, we are going to talk about the utility which in the quasi-linear domain takes care of both the allocation and the payment. So we have to talk about both these aspects, the allocation rule and the payment rule in the Pareto optimality. So let us get to the definition. So we will say that a mechanism f comma p1 to pn, which are the payments, is Pareto optimal at every type profile. So if at every type profile theta, the following thing happens: there does not exist any other allocation b, which is not the allocation given by this allocation rule f, and payments pi 1 to pi n with the following property. So it says that the sum of these payments should be at least as much as the payments given by the original mechanism. So this mechanism has this p1s to pn. Whatever they are charging, this other payment vector should charge collectively at least that much. And the following thing happens, that the net payoff of all these players in this allocation and this payment should be at least as much as the utility under this allocation f and the payment pi for all the agents, with this inequality being strict for at least one agent. So that says that everybody should be weakly better off, and there must be some player who is strictly better off. But why we needed this additional constraint? So notice that the property of Pareto optimality will be completely meaningless if we do not have any restriction. So notice this fact here. So if we allow pi I to be anything, then pi I can be a large negative, and in which case this will always be larger than the valuation, than the utility on the right hand side. So we won't have any control if we allow pi I to be anything. So that is the reason this condition is imposed, and now this becomes a non-trivial question whether there exists a social choice function, a mechanism which gives you the allocation rule and the payment rule to be Pareto optimal. Then it must be the case that payment that can dominate it extracts at least the same amount of payment that the original mechanism is extracting. If that is the case, then we'll say that this is so if this is possible to find, then this mechanism is not Pareto optimal. Actually it is Pareto dominated by this allocation and the payment pi I. But otherwise, if there does not exist any such allocation or payment, then we'll say that it is Pareto optimal. So we'll not go into discussing the examples of Pareto optimality because of the following result. We will actually show that it is actually equivalent to allocative efficiency. So we say that this mechanism is Pareto optimal if and only if it is allocatively efficient. So let us look into the proof, and that will give us the insight why these two properties, Pareto optimality and allocative efficiency, are one and the same. So let us first try the forward direction. That means we are given it is Pareto optimal, then we'll have to show it is allocatively efficient. We'll do in the following way, in the negated way. That is, if it is not allocatively efficient, it will not be Pareto efficient, Pareto optimal. So what does not AE mean? Not AE means that there exists some allocation, some B, which is not equal to the outcome of this function f, such that when you take the sum of the valuations of all the players at B, it is going to be strictly better than the sum of the valuations at f of theta, and this holds for some theta. This is what allocation rule f not being allocatively efficient means. Now because of this difference, we can actually define a factor called delta, which is just the difference between these two expressions here on the left and right hand side. And because because of this inequality, this difference is always going to be positive. Now the next step is to construct a payment which will actually beat this. So note that we will have to prove that it is not Pareto optimal. So therefore we have to construct one allocation which is B, and another payment which is pi 1 to pi n. So we are going to use the same allocation B, and for the payment we are constructing it in the following way. We take the difference between the VI B of theta I with the VI of F theta of theta I, and sum on top of that use the current payment and subtract out delta by n. This is our payment construction. So now let's see why it is actually satisfying conditions of the Pareto optimality definition. So we can see that if we rearrange these terms, you'll see that the VI of B of theta I minus pi of I, that is the left hand side here, and subtracting that out from the right hand side of that inequality is going to be equal to delta by n, and because this delta is positive, then this is definitely going to be positive. Also at the same time, if we take the sum over all these pi i's, we see that then there will be a summation over all these I in n's, right, for these two terms. But we know that that summation is exactly equal to delta by definition, and we are also summing this up for n times. So that two expressions will essentially cancel out, and what we will be left with is this sum over pi I is to be equal to the sum over pi. So it satisfies that condition. So it satisfies the condition it must be at least as much as the payment here, and it also actually gives the fact that this is at least as much as that one. And you can also see that it is going to be strict for at least one player. Actually the strict inequality is holding for every player in this context. So it is not Pareto optimal in this setting. So that is proving the forward direction. Let us now prove the reverse direction, where we are again trying to prove if it is not Pareto efficient, it will not be allocatively efficient. And this is a rather easier direction. So if it is not Pareto efficient, we already know that there exists a allocation and a payment vector such that this holds, and also this is holding, and this is strict for some j. Now what we are going to do is to sum over all this set of inequalities. What we are going to get is a strict inequality, because there exists some j in n for which this inequality will be strict. Therefore, when we take the sum, this inequality will also be strict. Now just properly rearranging this term, we get this inequality. So this is going to be different. So this is going to be strictly greater than sum over pi I minus sum over pi, and we already know by assumption that this is going to be non-negative. So therefore this is this difference at B, so the social welfare at B is going to be strictly more than the social welfare given by f of theta. So therefore f is not allocatively efficient. So now we know that the allocative efficient rule and the Pareto efficiency are the same. Now what we did not know that whether this efficient rule is implementable or not. Now let us get into that and try to find out a payment which implements the efficient allocation rule. Allocative efficient rules are actually implementable. So let us consider the following payment. Let us look at the second term first. So the second term here is actually summing the valuation of all the agents at that allocative efficient outcome. So remember that the outcome is maximizing the sum of the valuation of all the players, and that we are going to denote by f of efficient of theta. So now what is happening here is, in the second term, we are summing over the valuation of all the players except player I, and we are also subtracting that from the function which is not a function of theta of I. So this hi, theta minus I, is any arbitrary function but not a function of theta of I. So this is going to be the proposed payment, which goes by the name of its inventor, Groves. This is called the Groves payment rule. So let us look at one example to understand this point. What this Groves payment rule is. So suppose there are 4 players and they are theta 1, so there is only a single indivisible item which is going to be allocated. Either an agent gets it or does not get it. So if that player gets it, so here are the values that they have for that object. So for player 1 it is 10, player 2 8, player 3 6, and player 4 4. And when they do not get that object, they get it 0. And also, let's assume, because this is going to be an arbitrary function, we can arbitrarily choose minimum of theta minus I. If that is the case, you can verify that these are going to be the values of h1 to h4, and the payments will also be something like this. Why is it a little strange? Because in this particular case, there are lots of cases where the payments are negative. That means the mechanism design is actually paying the agent. But regardless, we'll show that this particular mechanism is indeed a truthful mechanism. And that brings us to the one of the very important results in the quasi-linear domain, which essentially says that the Groves mechanism is this Groves class of mechanisms are actually DSIC. So note that by changing hi of theta minus I, you can get a bunch of different payment rules. So therefore, all those payments are essentially falling in the class of Groves mechanisms. So we say that all such Groves mechanisms are DSIC. So how should we prove it? Let us go over this step by step. The proof is extremely simple, just that you need to know the notation carefully. So let us consider any arbitrary player I, and suppose that the efficient outcome when player I is reporting his type to be theta I and other players are reporting it to be theta minus I tilde, it is A. And when player I is actually reporting something else, theta I prime, then the outcome becomes B. Now by definition, we know that if you take the sum of the valuations of all the players, when player I has theta I and the other players have theta j tilde, where j is not equal to I, this allocation A, by the very definition of it, is going to be maximizing it. In particular, it will be greater than the sum of the valuations at B. So let us save this. This is one of the observations from the definition of the efficient allocation. Now let us look at the utility of player I when he reports his type truthfully. So theta I is the real type of player I, and he is reporting it truthfully. So this expression is the utility of player I. That becomes the left hand side. Now you can expand out this pi because this is going to be the gross payment. We write that down and we also have it here. Note that this is going to be, so this particular allocation, so when player I is reporting theta I and other players are reporting theta minus I tilde, this outcome is actually A here and here. Now if we club together this expression and this term, so we know that this is going to be the maximum for all such things. In particular, we can invoke 1 and say that this is actually going to be larger when player I has actually changed its type report to theta I prime. This has to be larger than that. And this expression hi theta minus I tilde is unaffected by that because it is not a function of theta I. Now again we can fold this expression back and by taking the second and the third term, what we get is that this is going to be the payment of player I when he is reporting theta I prime, and other players are reporting theta minus I tilde according to the gross payment rule. So that brings us to the next step, which says that the utility when player I reports theta I prime is actually smaller, at least as much as the utility when he reports it truthfully. So this inequality is crucial because of the fact that A is the maximizer of this sum. When we have this utility here, that is going to be at least as much as the utility when he misreports to something else. And because we have assumed this player I to be arbitrary, this argument will work for every I, and therefore we get the claim that this gross payment rule is actually dominant strategy incentive compatible.